This is Jim Tommaney joining you here. I'm happy to, and very excited to be part of the conference here. So again, my background is longtime data geek, experience delivering solutions with existing. Let me get my screen share going. Okay. So longtime data geek, basically responsible for delivering solutions with mobile analytics, health, genomics, telco. Previously architect of the InfinityDB storage engine, now part of Mariadb Column Store. My team is hiring. We're looking for C++ engineers with parallel columnar vector optimizer or optimizer experience. Contact me there, and locations. Limits of the evaluation. This is just a best faith effort exploration of what's going on with the hash join functionality across the distributions. It's definitely expected that different parameter settings could have different timings. And this is like one size, one data model, one data size, and changes to those things will change timings as well. And as always, test before moving to production. Some background on the setup. Basically, the versions I use: 8020, Mariadb 10.4.6, cloud environment with 64 gig memory, 8 cores. Data set involved was DBT3 at scale factor 10, which yields 1.5 million, 15 million, and 60 million rows in the customer orders and line item tables. Some parameter settings. I set the buffer pool size high, the join buffer size at 500 megabytes. Basically, all the operations would run from memory, and so all the timings we'll see will not involve reading from storage. Additional parameter settings used on the Mariadb environment. Quick note about the adaptive hash index. For this test, I turned it off. I was getting unusual timings. I would run a query, and then I would run an identical copy of the query on another table, and I'll get a different timing. I've got some notes at the back. We won't cover this, but basically the query could be either 15 seconds or 56 seconds. And it's hard to profile behaviors with that. So I've got that turned off for these test cases. Quick background on sort of just general expectations for hash join behavior. The index classic use cases, you can use an index access to identify rows in one table, join by a nested loop to another table, and join to a larger table as well. And the best behavior from a memory standpoint for that is when the large table fits cleanly in memory and you don't have to read from storage to access that table. Because it's a nested loop access, it has the chance of random IO happening. And then there's also another characteristic possible, that is block revisits. So you could have a couple rows within a block of data, and an index points to that, and it reads that from storage, and then later a different index lookup reads the adjacent row from storage, and those might not be at the same point in time. And so that's a place where block revisits can be a significant factor. So it works great when large table fits in memory. The classic hash join use cases is the idea that the small side fits in memory. And the extensions for that are around the Grace and hybrid hash join implementations that allow for the small side to be chunked up such that one piece fits in memory at one point in time. And so that's the classic use case for there. It works great as long as you can make that fit, but there's software allowing for larger small sides to progressively fit in memory with good performance. This is kind of the simplest possible world. It's just a simple self-join of order key, order key. It's a 50 million row table joining 50 million rows. This is a little bit artificial, and we're going to get into much more detail in the rest of the analysis, but just a quick setup for what I'm doing. Some timings on nested loop behavior, some timings on hash join behaviors. And we'll start to see the syntax used to drive the hash join behavior, which is to ignore the index. And in this case, I ignored both basically the primary index as well as any potential additional index that might be used for lookup. And then just for fun, I did the same thing with a skinny table as well. These queries, I happen to reset the adaptive hash index between each query just for additional timings, but the rest of the performance results come with AHI turned off. So quick note on this is that the join buffer size has a high impact on the performance characteristics, and especially for the Mariadb implementation. And so the blue and orange lines are the Mysql implementation that has the ability to take the small side and parse some of that off to disk and deal with that in a flexible manner. And so that has a very flat curve down here in terms of a wide variety of join buffer sizes have similar characteristics. The Mariadb implementation is highly dependent on the behaviors there, on the size of that. So we will come back to this as we get towards the end, but just a little quick setup. So these queries, and we'll take a look at the plans for these. And so this is just representation of the Mariadb in yellow, Mysql in blue, the syntax you see as you plan for these. So this is kind of more starting to get into real world situations. And these are what we'll spend time on today. It's basically, there's the idea of customer joining orders. So it's a smallest table to the medium table in our data set. There'll be across the top here, we'll look at an index join operation, which is no hints applied, allow the optimizer to select the path. The hash join scan, and what I do there is basically I disable all possible indexes on the table. And the reason for that is that under some circumstances, a scan feeded into a hash join can have a different performance profile than the output from an index operation feeding into a hash join. And so I've got that separated as a separate entry. And then the third one is a place where we, just a moment, where we basically just force the hash join behaviors. And on the left side, there's different use cases we'll look at. So it's basically customer joining orders. We'll have a query that filters on both tables. In this case, there'll be equal filters on both sides. So we might select, for example, 80% of the data or 20% of the data for the two filters. Then filter on the smaller side, and then filter on the larger side. And so these are different examples that we would look at under different conditions. And so we'll explore that. And just a quick note about this is that the expectations for hash joins is that it should be faster than indexes for some circumstances. I don't like the an evaluation of a hash join versus an unindexed join. That doesn't seem like something someone would want to do, and it's sort of like saying, well, it's better than nothing. And I think it's far better than that. And so that's kind of where I'm going here. Next slide here is, yeah. So the next one is orders joining line item. The structure is the same. It's just two tables that are larger in scale. Just some detail on the syntax that I use to execute this. Customer join orders, cus key equals o key, cus key. A hash join scan, where I basically force the scan by disabling all indexes. And hash join open, where I only disable or ignore the indexes involved in the join, the minimum required to force the hash join behavior. And so this is what we'll look at first is the query 1.1, 1.2, which is the filter on both sides. And we'll look at customers orders and then orders line item. Now to start to get into some of the data set here. So Mariadb on the left-hand side, Mysql on the right-hand side, customer joining orders, again, indexes on both tables. There's the idea of selectivity as a dimension down here at the bottom. So 5% of the data, 95% of the data. And in this case, the index is the clear winner in terms of performance across data conditions, across selectivity. The hash join doesn't have any places where for this query and for this scale data where the hash join is faster. There is one use case here where the gray line for MySQL is the index feeding into the hash join versus the scan feeding into the hash join, and that's slightly faster under certain selectivity. So this is the same join conditions but larger scale. It's now instead of 1.5 to 15 million, we're going to 50 million joining to 60 million. So the query's in place here. And here on the left-hand side, the Mariadb, we see something that looks very close to an ideal performance characteristics, in that we would expect at low cardinality, where the selectivity restricts the results to few rows, that we have great performance for the index, and that hash joins should tend to dominate at some position. And so that shows up very clearly on the left-hand side. On the MySQL side, I see some slightly different behavior. There's sort of a similar crossover point here, as well as it's in a slightly different position. But the performance differential is actually a little smaller. And what shows up for me is that there's a step cost at certain scale of the small side. And so if the performance curve was a little flatter around here, the performance characteristics may overlap. And this is just the plans available in support of these two queries, just to see the syntax used to demonstrate the hash join. So the next one is to apply a filter only on the small side, the same three hint conditions. And this is a use case where we'd actually expect, under many circumstances, for the index operation to be more successful. And we do see that. So there's no place here where the hash join is competitive under this situation. I'll talk a little bit more towards some recommendations at the end, but currently we say we disable access to the index, we ignore index, and for this specific query, the larger table, we only need access to the OCUS key column. And if we could do a hash join to a covering index that was run with a full index scan, that would potentially be faster. But because of the way the hint is structured, we can't have both our cake and eat it too. This is the same query scenario. So there's a filter on the smaller side, joined to the larger table. And we see there's definitely a sweet spot for hash join for both engines, where it has performance characteristics that are better. The Mariadb is here. And there's the idea that index is superior here and hash join is superior here. There's a similar trade-off here where it clearly becomes better, but I suspect there's the same step cost is showing up, and that's likely something about how the hash tables are populated or built in support of the hash join operations here. And to be fair, this is actually measuring different functionality. So the MySQL implementation has the gray/hybrid hash join that allows for saging to storage, and it could be that that's part of what's going on here. I didn't have the time to kind of profile the underlying implementation to identify what specifically was supporting that, but that's the behavior we see here. This is the third query, which is a filter on the large side only, and so it's coming in from the other side. Okay, so there's many things we're going to look at here. So certainly if you look at just the blue lines, these are the index access paths here. And there's definitely an inflection point for both engines. So there's an inflection point here and an inflection point here where something happens differently. And what happens is that the join order between the tables flips. It's indexed in all dimensions, but here, when you think about it, if we've got an O order key and we're looking for 10% of the data, then that's now, orders is 15 million, 10% of the data is 1.5 million, and now it's a coin toss on what is more effective. And because the index is on that key, that's likely to be a successful path. And so here the optimizer automatically flips the plan, flips the join order to allow for great performance under both use cases. under low cardinality and high cardinality use cases. Here, because it's sort of, there's an opportunity to drive from the using that filter. The fastest path is actually not a hash scan plus, not a scan plus a hash join, but instead to, oops, sorry. But instead to allow access here. So that's in place here. Okay. The ideal world might be something that looks like a progressive optimizer behavior where it actually doesn't show. I didn't measure a specific use case down here. So all the way down here at 0.01 or 0.001, highly selective access to the data, the index is actually going to be faster than the hash join plus the scan plus the hash join, or index lookup plus the hash join. Sorry about that. So way down here, the index is going to dominate. In the middle, the hash join operation dominates, and then at larger scale, the index operation dominates. And so that's an opportunity for potentially progressive optimizer behavior in place. And this is the same data scenario. So there's a filter on the large side. So orders joining line item, filter on the larger side only. And so this is a place where the hash join is clearly faster and clearly faster across a wide variety of circumstances than the index operation. Just a minor observation, the performance curve for Mariadb looks flatter at different scale as the selectivity goes up. And we don't see in the MySQL sort of that step cost because the small side build is static in this situation. So the orders table is a fixed size, and so that's set up that way. And some quick comparison on these metrics versus the smaller join, the customer joining orders versus the larger join. The nested loop cost went up by the elapsed time for nested loop went up by a factor of 10, and the number of rows being read and used to do an index probe went up by a factor of 10. And so there's a very clear linear cost associated with the index operation. The hash join at the lowest scale, at low selectivity, is about 5x faster. I'm sorry, 5x slower with a larger data set, and about 3x slower further to the right. And so that's kind of a data point suggesting that at larger data sets, the hash join is going to tend to dominate, and this just kind of reinforces some expectations up front. I did look at something that looks like a more robust query. So those were very simple in terms of the select count. The hash join has smaller responsibility for pushing records through the hash join operation. The amount of work done and the code complexity is smaller for a count star operation. And so in this case, I had a index operation where there's no hints in place, and then basically the query itself had the filters applied, had no index applied. And so it's going to be scan operations anyway. So we're really talking about just two use cases, an index operation and a hash join operation. And we see index at the very low selectivity being at 10% of the data being superior. It works better as expected. We do see a crossover point for Mariadb. We don't see the same kind of crossover point at MySQL. And my expectation is that this is sort of an expensive query, and there's many other costs that are introduced that may hide any differences in the performance of the hash join. And so it's something I would have expected some performance uplift, and we see a little bit in Maria, and not yet in the MySQL implementation. Okay, so we talked earlier about the join buffer size and the impact on queries, and we're going to use this query to do some more profiling. And what I mean there is that we'll run this query under two conditions at the 20% mark right here, and at the 80% mark right here. So I'll have that run that same way, and Then we'll profile the performance characteristics when that happens. And so this is the query itself here. And here's the 20% query, and here's the 80% query, and the performance characteristics. And it's definitely, that configuration is a sweet spot to allow for good performance with Mariadb. And it's actually, if you increase beyond that number for that query, it doesn't tend to get much different. But the join buffer size work allows for the best performance when it's large enough to support that operation, and the Mariadb will still be functional if this join operation size, join buffer size is smaller. The performance will just decrease. Let's see. Yeah, so you may need to hand tune the join buffer size for large queries. The Mysql is a relatively flat performance curve across the middle here. The fastest was about 8 megabyte on the size, but realistically anything above 2 megabytes had a pretty good performance characteristic. Same query, I just looked at, measured the memory utilization under concurrent workloads, 1x, 2x, 4x, 8x concurrent queries, running this 20% query, and we see the memory utilization in place here. And so there's a linear cost, more memory used for more concurrent queries. It's slightly more efficient with Mariadb. And the quick note about that is I actually set for this specific use case, I set the join buffer size up to, I think, 2 gigabytes. So it was artificially high beyond what's required for efficient usage for these queries. And the memory utilization was not a function of the parameter; it was a function of the query itself. And so it didn't use the memory that was potentially available; only used the memory that was needed in support of this query. And so the case is that if I look back at the customer orders line item table, the one where I didn't get what I expected, it's possible that I could find a join buffer size configuration that allows for better performance, but within the scope of what we're doing, that wasn't available. Sort of tuning recommendations for developers, DBAs. Try hash join out when the filter exists only on the large size. That's a clear use case. Try hash join out where the number of index calls from the smaller driving table starts to grow, right? So 10K, I'm sorry, 100K, or a million or more. The actual value depends on, quite frankly, many things. Characteristics about number of distinct values in the index, characteristics about table size, the ratio of the table size. So there's many characteristics. So it's not quite that simple. And then, if there's no index, no join index available, that's fine too. When we talk about hash join and data scale, there's definitely some correlation that larger data is far more likely to benefit from a hash join operation than a smaller data set. We talked about small joining large. As the data scale went up, we saw more conditions where the hash join was able to show performance, at least that are somewhere in the scale. And then again, back to the hash join size, it doesn't automatically allocate space. It allows for space up to that point. And so if your queries are well behaved and have a measured amount of hash join utilization, memory utilization, it's not a problem to set the value larger. But under some circumstances, if your queries are artificially are very expensive and there's a risk there, you want to pay attention to that. And the notes on MySQL use case. This is kind of what I have some recommendations on kind of next steps on the software, and so what further enhancements could happen in this space. So certainly in my opinion, ignoring the index is problematic. First of all, it's a manual effort, and if someone changes an index name, then that changes the int. It hides an optimization from the optimizer. So the full index scan isn't available because we've told the optimizer not to use the index. And then the other part that's a little scary for me is that if you've configured the SQL to ignore the indexes and the hash join is not available because of an outside reason, the the memory limit is reached or a parameter setting, then the query can run in a Cartesian join, which could be a very, very bad operation. And so that's, under some use cases that could turn, 20 seconds into 20 hours. Quick note, the optimizer did not appear to select hash join under any scenarios tested. Ideally, it would be able to select it when it was appropriate, and ideally, it would be able to select it for a given query based on the cardinality. And then some, possibilities around next steps for engineering around Mariadb and MySQL. Thank you, everyone. I appreciate everyone's time today and the chance to join the conference.